Hello, everyone. Thank you for attending. And today we have Dr. Kristijan from University of Fullerton, California, Fullerton. Today he'll be introducing us to a new software called CEO Convert ETABS to OpenSees. And I'm pretty excited about it too. So yeah, it's all yours, Kristijan.
Should I share my screen?
Yeah, go for it.
First, hi everybody. My name is Kristijan Kolozvari. I am an associate professor at Cal State Fullerton, but this project is totally separate from the university. So just want to make that clear. It's something I developed in my own time and started as a need for having a preprocessor for OpenSees, but then later I figured to take it to a level that other people can use it. So, okay, I'm going to share my screen. You guys should be able to see it. So thank you all for joining. I'm excited to give this presentation. There's more people than I expected. And feel free to mark down the questions and we can talk about it afterwards. Basically, I'm going to describe the software in maybe 20 some minutes. And then we're going to do a couple of examples, and I'm going to try to do them very in detail so I can demonstrate as much as capabilities as possible. But obviously, I can't cover every little thing that the software can do. So let's begin. Convert ETABS to OpenSees. I decided to give it the name of CEO, but it just stands for really Convert ETABS to OpenSees. It's not the only tool that does this, but I think it's a little bit different than the other ones that I've seen. And this is just a preprocessor, so it doesn't do any post-processing of any results. So as we just kind of chatted, Pavan and I, there's a lot of emerging software that you can use to post-process results from OpenSees. So this is only, again, just for pre-processing. So I just want to start with a couple of slides to explain the motivation behind everything. It's really started by finding this slide. I remember seeing this as a graduate student, like 10 plus maybe years ago. And really the number 3 over here, one of the main 3 topics, or one of the main 3 objectives of OpenSees is to develop new models to improve the analytical capabilities for researchers, but also to foster some kind of mechanism where the research can be implemented directly into practice and disseminated into industry. And this tool is kind of perfect for something like that, because as you all know, we have ETABS that everybody's using in industry pretty much. It's one of the most, probably the most used software in building design. And then we have OpenSees that's in academia, and there's kind of a gap in between. There's big sort of disconnect because engineers are always saying that, yeah, we heard about OpenSees, but we really don't have time to write our own code and figure out how it works. And in academia, really, ETABS, at least most of the time, is used for linear elastic analysis, although there is some nonlinear models recently. So it's kind of a gap in between, and this little tool is supposed to bridge that gap. At least it's gonna try to do so in a way. So especially with the development of performance-based design, as you guys all know, with tall buildings design, and also AC41 requires nonlinear analysis, and this need for nonlinear analysis is really just only increasing as the time goes by, and as our computers get more powerful and as the new models come out. So the nonlinear analysis really becoming kind of an everyday type of a task in engineering office as well. And then OpenSees, as we all know, is very, very powerful when it comes to conducting nonlinear analysis. So the whole idea over here was really to create a model in ETABS, and then have kind of a one single click conversion tool that will convert that ETABS model into the OpenSees model, but then allowing the user to use all the good stuff from OpenSees, all the new models, new elements to do parallel computing and so forth. And that's pretty much kind of the motivation behind it, to have something that will be easily convertible from the software that everybody's using into OpenSees, and allowing these new technologies to be used, and then have a way to kind of simply verify the design. So I just want to give a little bit of a general background, how the software works, kind of in the big picture, and then we'll dig into some specifics in a bit. So basically, it works in a very simple way. It takes certain information from ETABS model, and we will see in the next slide what that is. And then it takes information from Excel spreadsheet that is provided with the software, which is a little spreadsheet that has kind of a predefined tabs where you input the parameters for your nonlinear models, either that's a material or an element. So most of the nonlinear parameters are defined in this spreadsheet, and then basically combines those two and creates TCL input files. Currently, the input files are created in TCL. I know that Python and OpenSees Pi are being very, very popular lately. However, when you're using the CEO software, you really don't have to look and modify any of the, I mean, you can, of course, you can open the input file, but you don't really have a need to modify any of the input files. So it really doesn't matter if this is TCL or Python that the input files are for. And then kind of a very simple way to run the analysis. I think there's multiple benefits of this type of a setup. First of all, ETABS is very easy to use. It has a very nice graphical interface. Also, it allows very easy kind of a meshing, changing different element properties, creating geometry, 3D view, rotating your building or whatever it is. So that's really good, good about ETABS. Also, engineers and a lot of people, even the students, use and have ETABS in their either schools or at their work. So they're already familiar with the whole environment, and they don't really need to learn new software here, really. And then Excel, of course, is something that we all use. And also a good thing about Excel is when you want to enter a number of, when you want to enter parameters for a number of elements, say you have 100 beams in your model, it can be very time consuming and very kind of, I guess, time consuming, almost annoying, when you have to do something 100 times and there's a process you need to click around many times, and that just kind of takes a lot of time and effort. So if you have an Excel spreadsheet where all the input parameters are in a big table, then you can even program some formulas to connect the parameters, and you can very easily scroll them all down and define input for many beams, for example, beams or any other structural component at the same time. So these are really this is the kind of benefits of using this type of a setup. And so when it comes to really installation, it's very simple. Some people already maybe here downloaded the trial version. It's basically you just have to register and then you get a license key. After that, you download the OpenSees, or you can use the OpenSees, whatever OpenSees you like. It has to be a 64-bit, that's the only thing. But so the OpenSees is not provided with the CEO software. And then you don't even need TCL. All you need to do, if you're doing one of the recent versions of OpenSees, you can just download the TCL library, which is demonstrated right here. You browse to the library, and this comes with OpenSees download from the website. And then automatically you also have TCL. So you don't have to install TCL, you're all set after that. And you also don't need Python on your computer either. So it's just basically having this software, and then you use OpenSees and you use TCL library from the OpenSees website, and everything works. In terms of the capabilities, ETABS version 16 and later is something that's supported here. We actually originally I started developing this in version 9, so that actually works too, but I don't think anybody still has that on their computers. It's a very ancient version of ETABS, although I kind of like it. So it works with version 9, but technically version 16 and later was being tested and used. And so from the ETABS model, what's being used is the node coordinates, node locations, masses, and load. And for the elements, connectivity and some of the properties of the elements. We'll see that later. I'll make a few examples of how you define different types of elements in the models. So when you're using ETABS, this is the environment. I think everybody who uses ETABS is well familiar with that. And these are really I would say, 4 main tabs you will be using when you're creating models. And that's the same ones that are taking parameters from ETABS in the CEO software. So definition of different parameters, drawing, right? When you're drawing lines, area elements, whatever it is. And then selection, of course, if you want to select and modify something, and then assignment of different properties, loading, and so forth. So those are the main sort of ones that are connected with the CEO tool. What's really critical for the process and using this software is really this particular slide here that shows naming convention that's used when using this software. So for example, it depends how you give a name to a certain type of an element in ETABS, it will affect what type of an element is created in OpenSees. So for example, if I want to create a bar element, just a uniaxial truss element, I'm going to use bar and then I'm going to have underscore and put material tag that I want to assign to. Similarly, you know, you can see for the others. For example, if I want to use nonlinear displacement based element, I would have DBE and then an underscore, and then you put the tag of the aggregator. If you want to use, say, MVLEM wall model, you would put MVLEM and then tag of a section. So this is how software recognizes, you know, oh, I'm going to take area element from ETABS and I'm going to create a wall element, MVLEM, for example, in OpenSees. So that's kind of the system, how it works. Similarly, for different point elements, hinges, springs, and so forth. So this table kind of gives you a little bit of almost like a little cheat sheet or a little flashcard when you want to use this software, like how do you create different types of elements. It's also the elements, it's also for material assignment as well. When it comes to Excel input file, here we have a number of tabs that are currently available in this kind of most extensive version of the software, and you can create different types of materials. And this is just, again, a grouping. Of course, within one tab, you have multiple materials available. And we have some base isolation options here. We have, you know, line elements, we have area elements, and then there's some analysis settings for static and dynamic analysis, and then general settings, you know, about a convergence, what type of integrator you want to use, and so forth. So here's an example of Excel input. Basically, here we're looking at the steel input for nonlinear steel material, and all the other tabs, or I would say most of the other tabs are organized in a similar way. So what's important to note here is that you have kind of a switch over here. In this switch, you basically turn on and off a tab. You don't have, this is kind of not critical for the whole process, but if you have all the tabs on, then, and if you have some information in there, then the actual converter or the CEO software will create some materials or elements that maybe you don't need in your model that could create confusion. So it's a little, just a little option to turn things off if you're not using them, to keep your kind of model kind of nice and tidy. Then there's a drop menu where you can choose, in this particular case, different types of material models, and similarly for others. And then here is obviously when you put where you put all the input parameters. There's also a little kind of a box here with information that defines all different input parameters, just to kind of give you a reminder of, you know, what you need to put in order to define this particular material. And so you don't have to Google OpenSees, you know, user manuals all the time. And this numbers 1, 2, 3 is simply a number of the column over here. So it's kind of easy to relate one to another. So that's kind of like how the Excel sheet looks. And this is just one example. And we can now go and take a look at one of the examples here. I just kind of want to walk you through it and show you all the other tabs. So if we start all the way from left here, this would be, for example, for the elastic materials. And then this will be for hysteretic materials over here, because some materials have so many parameters, it's kind of a big tab, but basically you have all these different types over here that are commonly used. Then there's a little tab over here that you can use to calibrate your materials. It's kind of useful just to quickly get the backbone. How is it going to look like? And again, if you choose different material, you know, say I want to do pinching 4, obviously this is all going to get messed up because pinching 4 has a different set of parameters. But in this case, we had hysteretic. That's the last thing I was doing. So we can see this. So for different materials, again, you find here what the parameters you need to put in, and then you put them in here. And this helps to kind of just quickly, it's nothing fancy. It's obviously just Excel, but you can quickly see the backbone. And I think that's pretty useful. There's also a way, I haven't set this up, but to show parameters for AC41. Obviously, this is not matched with the AC41 parameters, and you can change the AC41 parameters over here in terms of A, B, C. So a lot of times we want to match or calibrate our materials in OpenSees with the AC41. So then there's this option to do that. So that's this hysteretic calibration tab. Then we have a concrete materials tab. We have concrete 01, 02, and concrete CM. Very easily, you can add any material over here. So if you guys need, or if the users really want to use concrete 06 or something like that, I'll be more than happy to add it. But from my experience, concrete 02 is kind of like what 99% of people use. Concrete CM is good because it has some unique features, but it's a little bit more computationally demanding. So I put kind of the bare minimum here that most of the people would find useful. But again, if there's a really strong need for some other material, then I'll be more than happy to add it. Similarly for steel, then there's an option to have a combined material. So, you can do the parallel materials or series materials. They're pretty much explained over here. And all you need to do is just put the tags of the two materials you want to put in parallel or in series. These numbers are actually just remain from my testing. So if I want to make, say, two materials that are parallel, I put their tags over here and they will be parallel. This tab is off in our example that we'll talk about later, so it doesn't really affect anything. Then similarly for MinMax material, if you want to, if you want to induce strength degradation at a certain deformational level, either positive or negative, you can do that here. So this will create another material with the MinMax boundaries. Then there's a tab to basically assign material tags to link elements. We'll talk about this in a bit. And then there's an option for friction type of models. So here you can define different types of friction models. And then also for the slider elements, we have flat slider, single bearing, triple flexion, pendulum, and so forth. Then moving on, here we have fiber patches. Here is a little macro that creates basically your fiber cross sections. I would be honest and say that it takes a little while to get used to use it, but once you do it, it's actually pretty simple. But the way you input these parameters, each of the fiber sections have to start with a number here, obviously going in increasing order, and then basically that's kind of the cutoff. That's how the software recognizes if there is a new fiber section. Then once you create a fiber, you want to integrate it or aggregate it, right, with other shear and torsional stiffnesses. So you can do that here. You can assign, basically, these will be the shear stiffness in Y direction, shear in Z. So you assign material tags to these behaviors. So if you want to have linear elastic shear, which is very common, then you would put just tag of an elastic material that is defined over here, which is what's actually done in this example here. So we were here. And then similarly for torsion, you can do like a GJ, or you can do a torsion where you assign tag of the material that represents torsion, or you can define GJ. There's also option to put a totally custom section. Sometimes you have a section of some kind of a random shape or that is not rectangular and then you can calculate moment of inertia and all the other parameters somewhere else, and you can put in these values here. So you can have a custom section over here as well. There's a frame with hinges element. Here you would basically define length of the plastic hinge and all the parameters for frame and hinging. It's an option if you want to use a custom section for the elastic part, or its section going to be taken straight from ETABS. So if you say no, the section will be taken straight from ETABS. If you say yes, then use a custom section that's defined over here. We have a quad RC, which is basically actually not still available in OpenSees. So I use this for my own stuff. There's a paper about this element that's came out recently, so this will be available soon. And then there's also, but also this is used to define the fixed strut angle material, FSAM, that can be used in some other models. Then there's a tab for layered shell element. That's also a pretty good element for reinforced concrete walls or slabs if you want to do nonlinear modeling with those. And then there's MVLEM, where you put in the fibers, different fibers for each element, shear flexion interaction MVLEM, and these are the three-dimensional models. And finally, static parameters. So static analysis will be like a pushover analysis where you define directions, different peaks, and so forth. We'll demonstrate this later on the example. And then dynamic analysis tab, where you define, you give basically the names. First of all, you give the directory name where your ground motions are. You put names of the files where the ground motion data is. You put a time step, number of points, scale factors, and that's pretty much it. And then finally, we have here settings. So in the settings tab, you have kind of all the settings for your analysis, divided like this into gravity, static, pushover, dynamic, time history, and mode. And down here is damping, right? You have Rayleigh damping, you have modal damping, you can turn it on and off. And you guys, if you're using OpenSees, you're familiar with all these different types of settings, algorithm systems, so you can kind of like, you know, choose different parameters over here and as you wish. So that's like a little walkthrough through this model input file. So I'm going to go back to my presentation. So we talked about that, and this is the user interface. It's almost barely you can call it user interface because it's so simple. It's very like 90s or maybe even 80s looking. But at some point, I actually tried to develop some more fancy looking user interface, and I realized that really there's no need for that because this tool is so simple to use that it just made everything more complicated. So I dropped it. I think this is almost like perfect. And once you get used to it, it's so simple to use it that it's just typing stuff on the keyboard really and then pressing enter. That's really all you need to do. So I can walk you through these basic commands over here. So the first thing, when you open it, it says, what do you want to do? You can create a new model, which will open like a search box where you find and locate, this is the model I want to work with. Then once you select that, you can generate the model, so meaning convert the model into OpenSees. Then I realized like if you change one thing in the model and you want to regenerate it, it's kind of annoying to type in all the input again. So I added this option. It's called the update model. So basically you just click U in this case, and it will just automatically does everything for you. Then if you want to start running the analysis, you say, I want to analyze the model. Similarly, because there are some kind of a few things you need to type in to define what analysis, what load you want to apply and so forth. And I found that was kind of annoying to keep doing that all over and over again if I want to just repeat something. So there's an option to repeat analysis, which basically just does and repeats all the steps you already entered in the previous round. And then these were just help and about and exit. So for example, this is just, you know, if you click, I want to analyze it, then there's another prompt that says what type of analysis you want to do. And then again, depending on what type of analysis you select, there's maybe a couple of more questions. And we'll see that how it works through the example. But all of it is just typing stuff on the keyboard, 1, 2, 3, ABC, and typing enter. So it's pretty easy. We already looked at all different materials and elements, but here's a kind of a summary of what's currently implemented here. So we have elastic no tension. We have few concrete, few steel. We have this combined, parallel, or series. We have min-max. We have, in terms of hysteretic, we have these materials, EPP, hardening, hysteretic, pinching. I actually added a couple more since this slide was not updated. There's also Ibarra models that are added here as well. And then we have different types of friction models and also elements for base isolation. And in terms of plane stress, we have fixed strut angle model, FSAM, and we have plane stress user material, which is used for the layered shell element. So this is kind of, I would say, materials that most of the people will need to model a building, right? And so this whole kind of software is primarily, for now, meant for building modeling. It's pretty easy to add any other material. The framework is already there. So again, if there's a strong need from sort of community or people who use this, then I would be more than happy to update whatever the needs are. In terms of the elements, there's different types of line elements. We have truss, VRB, and then we have two types of elastic frame elements, Bernoulli and Timoshenko. We have beam with hinges and fiber-based, which is displacement and force-based. In terms of the sections for the frames, we have elastic sections. There's, first of all, the elastic one is just grabbed from ETABS directly, so you don't have to do anything in Excel. And there's also an option to use databases of steel sections, which probably is useful if you're modeling steel buildings. And I will demonstrate how to do this for different types of databases. So if you want to use AISC or maybe Chinese, New Zealand, or whatever. Then there's also a custom section, as we've noticed. We have nonlinear fiber-based sections. In terms of the area sections, we have elastic shell and we have layered shell element, which is most of the time used for reinforced concrete. And then in terms of the area elements, we have these. We have these two wall elements and the shell element. And then for the point, we have support springs, we have nonlinear hinges, and we have slider elements. I forgot to update a slide. There's also for beam column joint elements too. So any other material, again, or element can be easily added. And now this was kind of a general overview. I'm not gonna go and explain input for every single element that I just numbered, but I do wanna spend a little bit of time just getting into a little bit more details how you define, say a point element or a beam element or something like that. So these are just examples of different types of elements. So for example, for point elements, we have these three options currently available. We have support spring, say if you want to do something like this, and then you want to define a nonlinear material. For example, if you want to use this for soil spring with 0 tension capacity, you can use appropriate nonlinear material, and then you will get that. So this is one application of this support spring. Then we can use the plastic hinges. We can do a moment hinge, shear hinge. We'll see how we can, define that later on. But basically, this will be like an internal hinge in the model. And then there is beam column joint based on the scissor model, which is kind of a most commonly used model for, or at least the more simpler one for the beam column joints. And again, where you define and assign a material that will now represent the behavior of the beam column joint. So the first thing you need to do if you want to define one of these point elements, first you define the nonlinear material. So one of these guys, right? One of these backbones, whatever you want it to be. It can be steel, concrete, it can be hysteretic material, it can be elastic, although there's probably other ways to do if it's elastic. So you define that first. And then in the link tab, which we've just seen, you assign and say to link number 1, I'm gonna use material 101. So that's the thing you need to do in Excel. And then you go to ETABS, and over there in the section property and the link property, you basically create a link with the same tag. So if it's a link number 1, here I'm going to create link number 1. And here is where you define the direction of the material, if it will be applied in the global X, Y, or Z direction. So depending on what it is, if it's a vertical spring, horizontal spring, or rotational spring, this is where you would define this. Then the next step, you go to the joint springs, and here now in the spring, again, you assign a tag or this is actually doesn't have to be the same number as the one defined earlier. It can be something else. The important thing is that down here, you would assign now that link 1, for example, to this particular spring element. So now you can then later on in the structure assign this point spring to a particular location. And depending if you're using spring, hinge, or joint, which is the three kind of flags, OpenSees will either create a support spring, it will create an internal hinge, or it will create a beam column joint. You got to be careful when you're working with these again, because different, I would say, flag, spring versus hinge versus joint in this case, will create different types of elements and different types of boundary conditions. But it's all kind of automated. So if it's a spring, what the software will actually do, because in ETABS you only have one node, it will duplicate that node. It will connect these two nodes with a zero length element. It will fix the bottom of this node in the direction that needs to be fixed, and it will release, and the zero length element will be in the direction in which you want to apply this material. So it's all kind of automated. It happens behind the scenes, right? All you need to do is really define a link here, assign it in a certain direction, and then define a spring with that link, and then assign it in your model. And we'll see this in the first example. This is kind of what it is. But in this particular case, when you're using springs, you can also, if you want to just create a linear elastic spring, you can also do it through here, because that's really what this is for, right? That'll be this example for springs. Is similar we can do for hinge or joint, where this tag over here will have to be changed to either hinge or joint underscore something. Then when it comes to elements, let's say line elements, this is how they're oriented by default. And there is a slight inconsistency between how ETABS and OpenSees are dealing with local coordinates. So this was kind of a tricky thing to figure out how to make it work too. And there was no way to make it exactly identical, but this is how, when you create a beam or a column, this is how their axes are oriented in the global coordinate system versus local. But then you have an option to move and rotate these axes. So if you actually assign a local axis to an element in ETABS, you can rotate it only currently for these angles over here. So 90, minus 90, and so forth. Then OpenSees will automatically also rotate the local axis. So that's already built in. So it's kind of automatically does that. You don't have to worry about it. So that's possible. And there's really two ways you can do this using the CEO software, either assigning an angle or assigning a orientation down here with respect to either global or local X or Y axis and so forth. So that's also fully automated. Software takes information from ETABS and applies this thing into OpenSees. The same way, end offsets. A lot of times we want to have a rigid end offsets if you have a beam column intersection, for example. So that is also fully automated. If you assign this to a particular line element, then OpenSees will, or the actual CEO software will automatically create the rigid end offset, and it will basically have this effect. In terms of the stiffness modifiers, this is something that engineers use a lot, right? We usually have a cracked section, so we have elastic section and we assign it a certain stiffness modifier, like 0.3, for example, this for beams or something like that. That's also fully connected. So if you apply a stiffness modifier in ETABS, CEO software will automatically multiply whatever the section property is with this particular stiffness modifier, and it will write in the OpenSees input file with a modified value. So you can actually fully use these capabilities of ETABS. You can do it two different ways. You can define the stiffness modifier when you're defining a section, or you can just assign stiffness modifier to a certain line element. So both of these ways, both of the ways that are available in ETABS, they're both compatible with the CEO software. Basically, software recognizes both and fully automates this process as well. So here is just example. If you want to define elastic frame element, you have an option to use Bernoulli and Timoshenko. Actually, in ETABS, default one is Timoshenko beam. That's what they have. That's why I decided to have two. But Bernoulli, sometimes it's easy and simple. So it's really depending on what you want. And in this case, kind of the keyword over here, I guess, it's frame T if you want to do the Timoshenko beam, or frame B if you want to do Bernoulli. So that's how they differ. And all you need to do is to define this section in ETABS. And you assign it certain concrete, steel, or whatever material. You assign it a certain cross section. Most of the cross sectional shapes are supported. And then you assign stiffness modifiers or mass and weight modifiers. And then you just convert that automatically converts into OpenSees elastic, either Bernoulli or Timoshenko beam with these, moment of inertia area and every modulus of elasticity and everything that's assigned in ETABS already. So that's also like automated. The software connects the material with the sectional properties and writes that one line of command in OpenSees. And this is the last kind of example, I believe, for this definition. So, and these are very common, right? So fiber-based elements, we have both displacement-based and force-based elements. And as you guys know, first thing you need to do here to define a section, then you have to aggregate it, right? To assign the shear, behavior, and torsional stiffness. So the way we do this thing, the keywords for the displacement-based or force-based elements are DBE or FBE. All of these other stuff is really not active in this case because this is now nonlinear fiber section. So stiffness modifier doesn't make any sense, but concrete material obviously will be defined in Excel spreadsheets. So you don't need to, the only thing really here that matters is the names of the keywords that you use here to create either a displacement or force-based element. And then in the Excel input file, you would create a fiber section. And then you would, in the next tab that we also seen, right, you will aggregate this section with the specific materials that are used to define shear and torsional stiffnesses or shear and torsional behavior. And then that's it. And then you just assign that to whatever line element you want in ETABS. And just one example of area elements. Here, when you're defining area elements, we have slab and wall sections. So these are the two options from ETABS that you can use. And these are the different keywords you can use to define the shell element, elastic, MVLEM, SFI MVLEM, quad, or layered shell. So for the shell plate section is just defining basically parameters in the spreadsheet and assigning it to a certain element in ETABS. Again, this keyword is essential. So shell plate _1 will be taking properties of this first section over here, right? So you got to kind of, this is how they connect the Excel and ETABS. So these section tags are something you want to pay attention to. Similarly for the MVLEM 3D. So for example, over here, if you want to do a wall element, this has a tag of 1. So that's also important, right? Because when you're creating this in ETABS, it will be MVLEM _1. And you assign factors for outer plate bending. You assign tag of a shear material you want to use. And then you define a cross section of a wall in this particular case, right? Where each of these columns represent one fiber. And for each fiber, you define a thickness, width, reinforcing ratio, and then you assign concrete and steel material tags here. And that eventually gets converted into the MVLEM 3D model in OpenSees. All right, so when it comes to boundary conditions, this is very simple. Whatever boundary conditions, like when I say boundary conditions, I mean restraints, whatever restraints you apply over there, like if it's fixed pin, whatever it is, it gets automatically transferred into ETABS into their fixities. So that's pretty straightforward. When it comes to a rigid diaphragm option, you guys know if you use ETABS, and we'll actually play with that a little bit today. You assign a rigid diaphragm to any diaphragm you want in ETABS, and that's fine. However, OpenSees requires to define a master node. So you create a group in ETABS, assign objects to a group, and that group has basically this name, rigid diaphragm masters, and then all the nodes that are in that group will be the master nodes of those diaphragms at that floor, and that's how you would define a rigid diaphragm. I'll show you that how it works later. And similarly for equal DOFs, if you want to connect two nodes with an equal DOF, you would create a group in ETABS. If you guys know, there's option to create groups, and you would give this name to a group, equal DOF. In this case, IJK really defines in XYZ directions how are these two nodes now related, and you can read the explanation here. You can really, do this in any of the particular direction, so you can kind of slay them together. Recorders. All right, so we're almost there with this explanation. Recorders are defined through ETABS groups, right? And that's kind of a critical thing here. And so in the assign objects to groups, you put a group name. And you have the node recorders and element recorders. We can, for the nodes, we can record displacement, velocity, acceleration, and reactions. For elements, internal forces, strain, stresses, depending on what that particular element can do. And here is again a little flashcard or cheat sheet where it has all the ETABS group names and the corresponding OpenSees recorder command. So if I want to record the displacements of some node, I would say node displacement _1, for example. This X really doesn't matter what it is. It's just a flag, so you can distinguish between if I'm recording nodes at the first floor, second floor, or whatever. So that can be anything, but it has to start with this string over here. And then that will create displacement recorder for any node. Similarly, for any other node recorder, you can, for hinges, for example, if you want to record the deformation of a plastic hinge, you would have hinge deformation, hinge force, or material response of the particular hinge. For drifts, here we have really useful automation, where for drifts, you could just select a bunch of drifts along the height, and they will be automatically reorganized from the bottom to the top, and it will create the drift recorders that will give you the results of the drift. So for example, if you do drift IJ, that means drift in I direction, and J would be a perpendicular direction, right? This is particularly useful compared to like Perform 3D. I know over there you have to define drift recorder for every story, and that's pretty time consuming as well. Here you can just do it in one row of nodes, and that will automatically do it. And same for everything else, wall strain, wall stresses. So these keywords are important. You create a group in ETABS, and you assign these different area elements, nodes, line elements to this group, and that will create a recorder in OpenSees for that group of elements. When it comes to loading, currently everything just works through load patterns. So you define that load live load pattern. Load combinations is something that I'm still working on, but eventually that will be too. So you kind of would have to manually, I guess, combine the loads. But most commonly, that's not an issue. And the CEO software supports all types of loads, joint loads, frame loading, and shell loading. So area elements. Not maybe all of these options are available, depending on what really OpenSees can do. So for example, for shell only, you can do uniform loading. For frame, you can do distributed or point load. And for joint load, obviously, it's to point force. So when it comes to mass, there's two options. You can either add additional mass at the joint, which is probably good enough for some very small model. But if you have a big building, then you want to use these capabilities of ETABS, where you basically where ETABS assigns or assembles the joints to the mass, joint mass at different nodes, and then you can directly drag that in to OpenSees. So that is actually quite useful tool, and you can use, you know, in the mass source you can define if you want to use element self-weight mass, if you want to do additional mass, or mass that is specified by load pattern. This really has nothing to do with OpenSees. ETABS will just grab these different pieces of information from the ETABS model, convert it into assembled joint mass, and then CEO software would just take the assembled joint mass and assign it to different nodes. When it comes to analysis, these are the standard things that I guess you would need. Gravity, displacement control, force control, and then in terms of dynamic, we have modal and we have time history. And we can run one ground motion at a time, or we can run multiple ground motions at the same time. And this is how they're combined in different sequences. So it's kind of like put it in a box sort of way that you always apply gravity first, and then you can do gravity plus modal, gravity plus this, gravity plus modal plus dynamic. It also calculates modal at the end of the ground motion. That's sometimes useful to see how much your building soften up, for example. So it will give you the answer and values of the building modal properties at the end of the ground motion as well. This will be the input for static analysis. So if you want to do a pushover or like a cyclic pushover, this is what you would do, right? You define direction, and then you define the peaks, plus 10, minus 10, plus 20, minus 20, right? So forth. And you define the increments, and then you run it. We already looked at this in the actual Excel file. So for the ground motions, you can apply the ground motions in any 3 directions. If you want to apply ground motion only in one of the directions, and then, for example, in this row number 2, I would put only ground motion X, and then everything is blank. So automatically we'll apply only ground motion in that one direction. If you want to do bidirectional ground motion, then you would put information in both of these boxes, and that will automatically recognize to apply them to both directions. And we already seen this in Excel spreadsheets. So this is different parameters for static or dynamic analysis. These are all the different types of settings that OpenSees allows, and it's just a simple drop menu in Excel. All right. So this took longer than I thought it would. Let's go to example number 1. So the example number 1 over here is just a very simple frame. It has elastic slab over here. I'm using here purposely, even though maybe this is not representative of real building, but I'm purposely using some elastic steel sections over here. And I'm using nonlinear beam column displacement-based element, so fiber section for the columns. And I want to demonstrate a few things over here, how it really, how do we assign materials, load sections, and so forth. So time to step out of this and go into here. So here's our example 1. So at the beginning, right, we have, this is only the two things that you need. You need Excel input file, which is the one that we just looked at. And then you need, obviously, your ETABS model over here. In terms of ground motions, we'll run them later, but since this is opening up, this is just a row or one column of acceleration input files. So here's my ETABS model, and this is basically a screenshot we have over there. These elements over here are this DBE1. So these are displacement-based elements, right? Those would be the nonlinear fiber. The beams are, maybe I should not use the extra, the beams are W2168. It's kind of randomly selected that. So that's, those are all beams. So that's a database, right? That's defined in database from the AISC sections. The slab elements are this shell plate 1. So that's a keyword to create an elastic shell element. And if I get out of this extruded view, I'm having also moment hinges over here and all these points that are assigned to this process that I described, right? So first thing, you define a link. So we have link 1 and link 2 for the two different types in two directions. So, you know, here I basically just assign the direction. This is going to be rotational hinge, so around R1. And I also assign a spring. I assign this link to a spring. There's link 1 to hinge 1. So if you take a look over here and point springs, this is where I assign those springs. These are the hinges, right? In actual Excel input, I defined here in the hysteretic tab, I have material, hysteretic material for beam hinge. So that has tag 101. I assigned that tag to link 1 and 2, right? And then I assign those links in ETABS. So that's for that. In terms of actual fiber sections, this is the cross section of the column that I'm using. So I define it here. In the aggregator tab, I say how many integration points. I define and assign elastic materials to the shear, and I assign some torsional stiffness. Elastic materials are 1 and 2, so this will be this one over here, 1 column shear, right? That will be our elastic stiffness. So that's kind of in terms of definition of different elements. In terms of the load, what we have over here, so I just applied, we're obviously going to use self weight of all the elements, and I applied just 150 pounds per square foot uniform load. That's the dead load. In terms of live load, there's no real live load here. It's just I'm applying dead load in this example, but I also have a pushover load pattern that I'm using. So, and I'm going to show you two different things, one with rigid diaphragm, one without. So for the rigid diaphragm pushover, I have only one load in the center of mass here. For the other type of pushover without rigid diaphragm, I have 4 forces in the corners. Let me turn off these hinges just for a second. So we got four forces for the pushover load. So those are the two load patterns I currently have. And then last thing, I want to show the mass. So I'm going to demonstrate two types of applying the mass. One would be with just additional nodal mass, and the other one would be with actually using the assembled masses from ETABS. So assigned additional mass, and here are the masses that I have. So I just added some mass at the corners over here. And that's the first case we'll do. Later on, we'll do the distributed mass that's pretty much at every node, right? So let's see, we have the columns, the beams are elastic hinges. I'm just saying a little checkbox here if I actually talked about everything. Load. In terms of the diaphragm, currently there isn't any rigid diaphragm. We'll assign that later. Oh, recorders. So in terms of recorders, if you go to define, group definitions, these are the different groups that I've defined. And these groups are, as I mentioned already, you know, if you use different keywords, they'll be used for doing different things. Most of the time it's for recorder, right? So I can select by a group. I want to just show you a few examples. So for example, control node. That's a node that you use to control your displacement, right? When you're running pushover analysis, you need to have one main node that will be used to control how much that node moves. So that will be, in this case, this node in the middle. If you reactions, I'm recording at all 4 columns. So this will be, these elements are assigned to this group's reactions all. So the important thing here, the keyword is reactions underscore whatever. It doesn't. Hinge, I'm recording displacement. For these hinges, I'm recording the forces of the hinges. I'm recording pretty much everything I can over here. Some of these groups are not for recorders. For example, P delta group, as you can see, has these 4 columns assigned to it. That means that this is how I assign my P delta transformation to these columns, by adding them to the P delta group. Here's an example of how would you define a, how would you record the formation of a fiber section. Fiber section, section 1, and then the formation. So that will be at, let me just deselect these. That will record fiber section response at a particular element. For drifts, this is only at 1 point. So here, if you can see, the drifts are recorded at these 2 nodes over here. That's basically how you would select. I'm not sure, didn't deselect them. I guess I forgot. So I select drifts. There's only these 2 nodes, top and bottom, right? And that will be a drift at that point. So drift xz means drift in x direction, and z will be a perpendicular direction to the whatever direction you want to record. That's how the groups will be defined, and that's how the recorders will be defined. So we're recording a lot of stuff here, and you will be seeing in the Excel or in the actual results when we run the OpenSees analysis, you will see these names of the files will be the same as names of these groups. Okay, so I think we're ready now. So currently we don't have a rigid diaphragm. We have 4 point masses in the corners, and we just start software. It's pretty again, simple user interface. So currently I'm selecting directory that doesn't exist anymore because I was playing with it. So you just navigate to this example 1. I'm going to copy and go over here. You select that folder, right, where the example is. That will be example 1, not the ground motions. You select that folder, you say OK. Oh, you have to save ETABS first. Sorry about that. So we browse, example 1, select, say OK. And the next question, and let me just, I want you guys to see both things, because the files are going to start showing up here. It says, would you like to create ETABS model, OpenSees model? Because there's no one in here, you say yes. And it's processing nodes, frame, area elements, mass. And you can see how slowly the TCL files are showing over here. It takes, I would say, I don't know, 5 seconds maybe or something. Here you go. So the model is done. We can press enter to basically brings you back to the original menu. And here are our OpenSees input files that are created. This is the main file, the model file. So we can open it. I can walk you through it just quickly. So basically, it's organized in a certain way that's kind of logical, I guess. So first we have nodes. Here are the 4 masses at the 4 corner nodes. And then you have all the node coordinates. Here's the 4 fixed nodes at the bottom. And then materials are defined, sections are defined. They're aggregated. Here we have elastic section. Here's our slab elements that are elastic slab elements. This is just different definition of geometric transformation. This is used for rotating it different ways, plus -9, but we're not doing that right now. Here, everything is by default. And here we have our elastic beam column elements. So these elastic ones correspond to those steel beams. So these will be the properties of the W sections. And And here we have our displacement-based columns, which is basically related to this aggregator tag up here. So fiber section 1, fiber section 2, these are assigned, here's 2. So we are assigning the number 2. We have these hinges, zero length elements, as I said. So this is this automation where you really, when you define a hinge, right, it's a moment hinge. For each of the hinges, the software creates these 2 lines. It has the equal DOF to connect the 2, makes a duplicate node, connect them in a way so they're connected fully together, except in that degree of freedom where the hinge is, in this case, and then applies the hinge in the direction 4 or 5. And here we have recorders. So you probably recognize some of these numbers, some of these names, reactions, all, node displacements, control node, and all the recorders are written here. So that would be the main input file. The load patterns are all saved as separate files. So here, for example, we also had, I guess I forgot to show that, but we had some element load, like a beam load. We go back here and we can display frame load. So we had the self weight of the frame elements, right, assigned as line element, as line load. So those are these element loads in OpenSees, beam uniform loading, right? And then all the distributed area load is converted into point force on the slab, and those are all these remaining forces. There's a little kind of automation that calculates tributary area and assigns it to a node. So that's the model part. Now we want to run some analysis with it. We say analyze, I click A, and then what kind of analysis do you want to run? Well, let's say I want to run the displacement controlled analysis, which is like a pushover analysis. Before I run it, right, I want to make sure that I understand what we're doing here. So here I'm running a pushover in direction X, which is 1, up to 8 inches of displacement. So that's my peak. And increment of, to get to the 8 inches is 0.1 inch. So, okay, let's run that. So I'll click 2. You just give a name to a folder with results. So I can say pushover in X. And then it will ask you a couple of questions. What's your gravity load pattern? You say it's number 1. What is your pushover load pattern? In this case, we don't have rigid diaphragm. We have those 4 points. So I'm going to use number 3. And do you want to run it? Yes, I do. And then you can visualize or not. It's really not critical, but just for fun, we can say, yes, I want to visualize the model. You can already see that the blank folder is created here. This is where all the results are going to be. And then we say, yeah. And you can see the gravity is applied and the pushover. Trying to go back into this window. At the end, first of all, if we didn't visualize the model, you see the progress here, right? And then it tells you if it had to go to like a resolution strategy, like if it failed to converge, that will record how many times it had to do that. There's total analysis time, in this case, 21 seconds, and then press enter. If we want to say, I want to change something real quick. So let's say I want to push it to 8 inches and push it back, or push it, kind of a cyclic pushover. Then you just add a few more lines over here. So my other peak will be, say, -8 and then 0. Let's do that, right? And then we have to put the increments here. So this is what we want to do, right? We want to push it back, forward 8 inches, backwards 8 inches, and then back to 0. We need to save this. And then now I don't want to say A. I don't want to analyze it because I will have to, plug in all the gravity load. I have to do all the punch in all the input parameters that I already did. So if you just want to override results, all you need to do, say I want to repeat the analysis. You put R and it will do all this kind of stuff for you. And I guess it'll be fun to see how this goes, but here's the first sequence, second sequence. Now, sometimes maybe, converges or struggles a little bit. That's now the OpenSees thing, but keeps going. I'll actually rerun it so we can see how it moves. I guess that's always fun. So we got to repeat and visualize. So we go forward 8 inches, we go backward 8 inches. This is the part where it gets a little struggly, but then it keeps going. And all right, so that's that, right? That would be a pushover example. You can obviously this type of pushover is used a lot when you push something back and forth, especially if you want to validate your model against some test, right? That's what we do very common. So I find this very useful for that particular purpose. All right, what I want to do next, just to demonstrate some changes in the model and how do we do that. So for example,
Kristijan, sorry. Do you want to take some questions before?
Let me just do
the
5 more minutes.
Yeah, okay. Sorry, because I have another meeting after this and I have to run. And I didn't want to disturb the session. Sorry.
Okay, then jump through the, let me cut this a little shorter there, then I guess. All right, so let's say that I want to assign property. I had a kind of a sequence what I wanted to show here. Let's say we want to assign some different types of sections. Let's say you want to do Chinese section, right? And you select some kind of database here. Let's say this section over here. All right. And then assign, well, first of all, I'm going to select all my W's and change it to this. So select by property, frame section, select this one, and then I want to assign that, right? Okay, so in order, if we want to now update the model, all you need to do is you say, I'm going to update the model U. Now, here is going to report an error because this database is not automatically plugged into the software, but it's very simple to do, and this really works with any type of databases. You just have to go and copy the one from hold on, the navigation pane. So you go to program files, right? You go to where the ETABS stores all their stuff. You go to the libraries, and here you take the Chinese one, right? You all you need to do is copy it inside of its model, and then it will basically automatically do it. So let's say I want to update the model now. And you can see that it loaded all the sections from the database. And it's going to just update the model. If we go to model input file, we'll just reload it. All right, so that's that. And I want to just show one thing that I think it's very important, and I want to take some questions. Sorry about that. It took a little longer. There's a lot of stuff, and I guess I just got too excited, carried away. I just want to show you one more thing. Well, I was going to show a lot of things, but I guess I need another 1 hour or something. Let's say you want to do a mass that is calculated by ETABS, right? Then here in the mass source, you would basically select the element mass, and we don't want to use these additional masses that we added. We want ETABS to calculate automatically the mass for everything. So you would select element self weight. Now, once you do that, obviously, you first have to let ETABS calculate these masses. Currently, they're not calculated. So you need to analyze your model first. So I'm just going to run quickly only the modal analysis over here to basically just let ETABS assemble all the masses at different nodes. And then once that's done, here it is, then I'm going to just update the model again. And now you can see that mass source is used. So the ETABS is basically calculated the nodes, and the CEO takes all the node information from 73 different nodes. Basically what it does, if you go to tables, it takes all these nodal mass that's calculated by ETABS and assigns it into OpenSees. And if you take a look at this, we scroll all the way to the top of the model, you can see that every node now has a mass, right? So that's pretty useful. We're calculating mass, you don't have to do any calculations. It all rely on ETABS. And one more final thing. Now we have the model. Let's say we want to run dynamic analysis. And that would be option number 5. You select the gravity load. And I'm going to jump right into the kind of the case where you can run one ground motion at a time, but let's say we have here 2 ground motions. If you go to the input file, dynamic, I have 2 ground motions. And we're going to try to run option 2, analysis on the multi-core. So basically running 2 ground motions at the same time. And analysis is started over here. And we have both ground motion results here, and they're all now plugging along. And here are all the results that we selected. So that would be dynamic analysis. Also separately, there are modal results. Every time you run dynamic, it runs modal analysis first. So here you can have your eigenvectors stored. Now that's just for plotting. You really want to have the modal analysis results where you have your periods, mode and mass participation factors. All right, I'm done. I was planning to show more, but I think I got stuck on the first section a little bit too much, and then
yeah, I mean,
examples are really what's important. But maybe next time or something like that. I'll try to give one example and then maybe upload it on the YouTube channel.
I mean, yeah, or I mean, I can always ask you for another session, right?
Sure, that'd be great.
No, that is always the possibility. Unfortunately, it's okay. Sorry for the apologies for that. But
yeah, if there's any questions, I'll be happy to answer.
Yeah, I mean, any questions? First of all, thank you so much for going over. And I mean, any questions from anyone on the audience? Oh, yeah. Hi, go for it.
Okay, thank you so much for the nice presentation. Actually, I appreciate that you took the time to explain every step so that I think at least for me, I had a complete picture of what you're trying to do. So for example, if I want to do something like IDA, incremental dynamic analysis, is it like I have to go to the tickle transcript and add few more lines, or is there a way to do it in the Excel itself?
Currently, there's a way. I get a lot of actually exactly the same questions. So I start maybe thinking like maybe I should try to add something to it. But currently the way you would do it, it would be a little bit of, it's possible, but it's not, how should I say, fully automated. First of all, for IDA, you use like 22 ground motions, if I remember that, or whatever the number of ground motions is, right? So the way you can do it, you can, for each ground motion, create a separate input file, right? Basically, you would copy this file, this model input file, and let's say this will be just for one ground motion. So if you have 10 ground motions that you want to run in the IDA, you would create 10 input files. And for each input file, this will be a different ground motion. And so if this is ground motion 1, then all of these will be ground motion 1. So it'll be the same ground motion. And the only thing I would change is the scale factor, right? Because in the IDA, you scale it up. So here you would use 0.1 scale factor, 0.2, 0.3, and so forth. And because this is Excel, right, you can just do this and write these, and then these will be all the same ground motion. Right? And everything is basically the same. So this will be IDA for one IDA curve for one ground motion. And then because you have, say, 10 ground motions, you would have to create separate input file for each ground motion, but that's totally fine. If you have multiple input files, you just select which one you want to run and the software will run it. So it's possible, but you would have to kind of multiply the Excel, which is, I don't think it's a big deal.
Okay, thank you so much. I might be wrong, but I think you showed for the post to see the result of the analysis, you used ETABS as an interface, or do we need to use another tool? Like, for example, the lateral, the deformation in force recorder, like you saved.
Create your own little either MATLAB or something, like all the results are here, right? So this is displacement, but you have to create a MATLAB code or something that plots these. There is no post-processing here. This is just a pre-processor. But we just talked about it, right? There's some Python tools. There's like a lot of things. With OpenSees, there's so many things different people want to process that it's kind of hard.
Yes, I mean, given, for example, your initial motivation, right? People in the industry, like you said, it overwhelms them to use multiple multiple tools for different things, right? Everyone wants a one-stop kind of solution, like integrating it with also the post-processor.
Yeah, I think that would be good, but currently this is just for pre-processing, and that's kind of what the idea is. Anything else?
Oh yeah, we have another question here, couple of questions actually.
Executable and Excel input. So if you go to the website, which is ceostructural.com, which is over here, you can see a lot of things over here, particularly, well, first of all, let me answer the question, right? In the downloads page, here is where you'll be able to download all different versions. Currently, there is this limited trial version that's just, it's basically everything you see here, but with some limitations. As soon as I release the full, version and the other versions, there's going to be beginner, student, professional, and it can always be customized. Then the trial version will become professional. Currently, the trial version is just the simplest one, right? And it's going to be by the end of the year, all this stuff is going to be available here. So you download basically the manager from here, and then you can watch the video in the user documentation. There's few YouTube videos about installation, and then there's few examples about kind of a simple model here, how to run the pushover, how to run the modal and dynamic. So there are a few YouTube videos on this user documentation page, and also the user manual in PDF can be downloaded from here as well. So check out the website and then subscribe down here at the home. If you guys want to keep up with the updates, you can put your email address. I don't ask for anything else, just the email, so I can keep you up to date. And also any questions can be directed from the contact form.
Yeah.
Or you can email me directly at CEO software at, I can put the email address over here, but basically contact form works.
Sorry, did you address the, sorry, I was reading another question.
I did not. So this will be the CEO executable. You would be downloading from here, this file, and then this one will ask you, you would have to run it. Now in this case, and then you have to register, and then eventually you download the CEO executable. So it's a little installation process, and there's a video how to do that in the user docs.
Sorry, I had a direct message.
You have ETABS template. Yes, the template. So once you download it, it comes with an example file, which is actually very similar to the one we've just looked at here today. And as a part of that example file, you have the ETABS template and you have the Excel template as well. Yeah, it all comes together with the user manual.
And I have one other person asking me for, what is the contact email for sales and how to use CEO if my model is created using ETABS 19? And finally, Dr. Kristijan provide his email for future questions.
So one at a time.
So what is the contact email for? I think they can get it
contact
from
email, you guys just subscribe over here. You can contact through the form on the website. You can also subscribe down here, and I will send you guys an email occasionally, and you can get it.
How to use CEO if my model is created using ETABS 19 already?
Oh, this is ETABS 19 that I'm using in this example, so it all works fine.
I think what they're asking is you created this stuff in Excel, right? And then you exported kind of it. And if they have already an existing ETABS model, can they use the CEO thing to analyze?
They can, but they would have to modify it a little bit, just like we talked about today, in order to, match the keywords of the different sections and things like that.
Yeah, I guess like that will give them the confidence of, if they already have an existing model which ran, and then with the OpenSees, they can check their own results. I don't know why, but it also helps them, I guess, right?
Yeah, sorry, I'm typing here the email address, the software element. So that's the contact information.
Okay, and yeah, the third question was that. So yeah. And any other questions?
The geometric transformation was handled automatically, right, by CEO?
Yeah.
Okay, interesting.
Everything is automated. I've been working on this for like 4, maybe 5 years. So there's a lot of things inside of this little, very kind of simple little program. There's a lot of things that are automated. Of course, I didn't work on it constantly, but I've been collecting a lot of input information, understanding what people need. So I think it's pretty comprehensive.
I was about to ask that question, so.
What was that?
I was about to ask that question. How long did it take for you to make this one?
Yeah, it really connects a lot of dots and creates OpenSees. I used it on many projects, but again, maybe we can have another meeting. Obviously, I don't think I covered about half of what I was planning to. Maybe I was just too wanting to do too much.
And maybe like next, we would also like to know like the background, how you actually did it, like the ETABS, the communication between ETABS, Excel, and the OpenSees thing. That would also be interesting, because
I'll think about a way to get
dumb
more
it down.
Maybe I should record my own videos additionally or something like that. But whoever is here, if you guys just subscribe and follow, there's YouTube channel, there's Facebook, there's LinkedIn. So just kind of like sign up there and you'll keep up with the dates.
Yeah, and I had a couple of questions. What are the kind of challenges you faced, like when making this whole thing, like, interface like between different things, the big things? One
of the challenge was that OpenSees is very sensitive software. Like there's a lot of little things that have to be perfect in order to work. Some connectivity. So for example, if you're duplicating a node, like which node is master, which one is not. There was a lot of little complicated things that it seems simple now looking at it, but there's a lot of complicated stuff going on in the background to actually make it work. So transporting the node coordinates and things like that, it's simple, but putting it all together and converging and making it kind of stable, that's what I spent a lot of time. But again, I used it on a couple of projects. Here's just one additional example. We've done it for the whole building over here, and we post-processed this in ParaView, and this is the type of analysis we did with this tool. And here we have also, everything is fiber element, everything is nonlinear, but obviously it all converges and it works. So it's a powerful tool. It looks very simple, but it can do a lot of things. So,
and another quick question is like, how about like, for example, if someone wants to do sensitivity studies or parametric, again, same like idea, you have to create multiple Excel sheets.
You have to create multiple files.
Okay.
Right.
Yeah, this was another one for me. Version updates if new materials come. For example, I'm using OpenSees, whatever version. Whenever I download like the
latest one, yeah.
If, for example, OpenSees have like 10 materials, I see like 2 or 3 materials. So you have to update in CEO, like
I would have to update.
Then only I can use them.
Yeah, currently,
Okay.
I would develop this with an idea that what would the kind of engineers or something in an engineering kind of universe.
Yeah.
Like it's not, you know, obviously OpenSees has hundreds of different materials. So again, if there's a strong need for some particular material, I'll be more than happy to add it. It's not that difficult. Yeah.
So you have to add so that the tool can actually access it and people can use it, right? Okay.
Yes, or I'm thinking about making so it's not really open source, but so people can have a little tab where they can add their own things.
Okay.
That'll be, I think that'd be great.
And oh yeah, go for it.
Sorry, in the material calibration, you have like certain materials. Say, for example, when I do calibration, like do I input just, you know, like I have to tweak in some parameters, right? Depending on which model I use. So do I do it automatically in your platform, or do I need to come up with those coefficients and then just
come up with the coefficients? Yeah, you have to kind of know what parameters you want to put in. This is just the framework where you put in the parameters, but what these numbers should be, that's on you.
So for the material tester, I have to use something else.
Yes, but there's a lot of these material testers for OpenSees available already, so I don't think that's a problem yet.
Yeah, I'm just trying to understand.
Yeah.
Okay.
And
thank you.
One other thing which understanding this is, so if I want to use, for example, coming from an industry perspective, if I want to use this, I still need to know OpenSees have knowledge on OpenSees, right? So that I can use materials and different things. And I also need to have idea about ETABS too, right? Like so that I can use things. Am I right?
I think ETABS is kind of like what everybody in industry knows how to do.
Yes.
In terms of OpenSees, yeah, you have to get familiar with models, but you know,
you don't have to code, but you need to know the idea, right?
Yeah, you have to understand the knowledge. I think it's more like a nonlinear analysis type of knowledge. You know, obviously, I mean, if you want to do stuff like this, and then, you know, just get familiar with these parameters. This is why I put these pictures and explanation here. You know, basically, you know, here you can see what parameter means what, and then you decide what number you want to put in.
Yeah. Okay. And one more question. I mean, I was writing down all the list of questions I had. So,
of course, yeah.
And the other thing which is like, when you are working in industry or stuff, like you want like foundations to be included too, right? Because piles are the foundations to be included, like piles or PY springs, because that is very commonly used to. So PY springs is very, very common to use.
So you can do something like this for the spring and the foundation. No, and you can apply it in different directions too.
PY springs are going to be much more, right? Like along the length of the pile.
Originally, this is all just for buildings. I mean, I didn't think about modeling soil structure interaction with this software. I do think about doing the same thing for SAP, and SAP would maybe be more along these lines, but obviously all these things are a lot of work. So
the reason I'm asking is like because like as you said, like people are like, the industry is demanding more nonlinear analysis. It's also demanding to include more of the soil structure interactions and all those things too, right? So I mean,
the way I've seen so far, most of the time soil structure interaction is just using using some kind of springs at the base. It's not nothing like super sophisticated. So
I just was curious if there is a trick to implement that too in this, like in a tricky way?
It will be a way through this. You can add a pile, I mean, as a separate story in ETABS, and that could be your pile, and then you can add little PY springs on the side. You can totally do that. Yeah, that's possible for sure. Yeah.
Yeah. Okay, cool.
So if anybody here has if you guys have a question, shoot me an email. If you want me to create some kind of an example, say, oh, I'm doing this in my master thesis or something, and I want to have an example of how to do that, I'll be happy to do it. And then maybe I'll spend time and record my own videos and put them on the YouTube channel of the CEO. So, you know, currently there's just this basic example. This is all very new and very fresh, and so things are coming out slowly. So if you guys are interested, there's a free trial. It's pretty limited, but you can play with the model that is similar to this one. Also, if someone wants to just validate one column or one beam or a wall, this will totally do the job. It will be very, very simple thing to do. So there's kind of different levels I envision for like students who are doing some simple things, and then for like engineers who want to do the whole building or something like that.
Makes sense.
Anyway, I'm really looking forward to any feedback here, and you can feel free to also email me, because I want to know what's needed, and I want to try to address the needs of the users. So.
Yep. Any other questions from anyone? I asked all my questions, so.
All right, I think I've showed most. I mean, you know, there's a lot of things. I wanted to show another example, which was this other building that was kind of a big building, but I think we're better to do it some other time, maybe, or something like that.
Yeah, I'll contact you again next time.
Yeah, no rush. I mean, we can do it next year. I know that's pretty busy.
It has to be next year for me.
Yeah, of course.
Yeah, and yeah, I mean, I really appreciate your time, Kristijan, and sorry.
Appreciate the invitation, and I appreciate everybody showing up here and staying for.
Yeah, and hours. Sorry to interrupt in the middle, unfortunately, today.
It's just a lot of stuff to explain, and you know,
it is.
Time goes by quickly, so yeah, we'll make it up some other time.
Yeah, sure. I'll contact you again, like sometime for another session where you can go over like more complicated examples, and also like the background if possible, so that like people like me also will understand how complicated it is to make such, I mean, appreciate these tools better, I guess. So yeah, well, sure, I'll be happy to do that. Yeah, and I mean, thank you so much again for your time, and thank you everyone. Stay safe.
And
thank you very much.
Feel free to send me an email, and I'll respond as soon as I can.
Thank you.
Thank you.
Have a good day, guys. Yeah.
Bye-bye.
Bye.